Okay, we should all have this data open. It should look roughly like this, right? And let's do something really quick. So here are our variables that we have. I'm going to walk you through and tell you what these variables are. But in order to do that, let's flip over here. Under label, actually, before we do that, I'm going to show you why I'm going to change this. If we go analyze, regress, linear, and first of all, I don't know what any of these variables are except for yak tote and audit tote, right? If it looks like this, you can left click and say display variable names, and then you can see what the names are. The problem is if we put in DIRs and alls here, and we run a regression analysis, the variables that it gives us, they still say mean unstandardized item, right? And so we don't know what we're actually working with. So let's do this. Let's come back to our data. Let's click on variable view. Under label, let's just make our labels say the same thing as our names. Just type in age, hit enter, biological sex, enter. Aim is an affect intensity measure. It's a measure of how intense you experience moods. Say that again. Oh yeah, you could do that as well. Yep, I'm only doing it because I'm just like walking through and telling you what they are. PBS is protective behavioral strategies. This data set comes from a sample of college student drinkers. And protective behavioral strategies are behaviors that you can engage in when you drink to reduce the likelihood that you'll have alcohol-related problems. Just FYI, I'm a substance use researcher, and basically all the data that you're going to see is going to be substance use related data. Audit, tote, is the alcohol use disorders identification task, or test, I think. It measures your level of alcohol problems. Mindful is a measure of mindfulness. DIRS is difficulties in emotion regulation. ALS is emotional instability or affect lability. Not that you guys are going to remember any of these. DTS is distress tolerance. YAC, is another measure of alcohol problems. And then drinks is kind of a standard measure of amount that a person consumes. So if you change those, then when we go to run our analysis, the variables will actually be there and they'll look the way that they're supposed to look. The first thing that we're going to do, you'll have to forgive me, I'm going to flip back and forth here, is we are going to look at I'm sorry? Did somebody say something? Let's look at redundancy first. So, in order to look at redundancy, no, I don't want to save that. In order to look at redundancy, we are going to, first, we're going to look at, let's go analyze, regress, linear, and we're gonna predict a person's ability to tolerate distress. This is often thought of they do some laboratory tasks associated with this. So for example, you might put your arm, this is a scale, just FYI, but you might put your arm in like cold water, and it's how long can you keep your arm in cold water? It becomes very painful, you know, or how long can you tolerate, I don't know, being shocked. But this is a measure of distress tolerance, right? And let's do this. Let's go difficulties in emotion regulation. And then we're going to do something here. We are going to hit next. And we are going to add affect lability. What this will do is it will run our regression in 2 steps. In the first step, it will tell us the relationship between DIRS and DTS. That will be a basic correlation. The second one will tell us the relationship between DIRS and ALS and DTS. And we will get the beta coefficients, which are the independent predictive levels of each of the independent variables predicting variance in the dependent variable. But let's do something else too. Let's click in statistics, and let's do R-squared change. Let's grab descriptives. This will give us means, standard deviations, variances, part and partial correlations. And we're not going to worry about collinearity diagnostics, and we're not going to worry about residuals right now. We are not going to worry about plots either, but you can come in here and you can build the plots. We're going to talk about this next class when we visualize data. All right, so does everybody have that? Has everybody done that so far? Hit OK, and let's have a look here. So we have 670 people in this data set. Here are our means, here are our standard deviations, and these are uncorrected means, right? Down here, we have our basic Pearson correlation coefficients. So it's worth noting that the correlation between DERS and DTS is minus 0.521, and ALS and DTS is minus 0.392. And this is also really important because DERS and ALS are really strongly correlated, right? Okay, let's keep moving down. Oh, did I do this wrong? No, I did it right. All right. This gives us our model steps, and you can see that the R-squared is 0.272 and 0.272. What does that mean?
There is no explanation of variance above and beyond DRS.
Yeah, right. We're going to see that when we get down here, but DERS and ALS, despite the fact that, look at, that's a very... this is a strong correlation. It is statistically significant. These are our p-values. Hey, just as a quick refresher, what is our cutoff for statistical significance, just kind of broadly in science? 0.05, right? And so we see p-value here of 0.000, and that means it's less than 0.001, right? And of course, p-values, they can indicate a magnitude of strength, but also they're highly influenced by what? Sample size, yep. And so the larger your sample size, just the more likely that you're going to have. 670 is not bad, and you can, the nice thing is a correlation is a measure of effect size, right? And so what percent of variance in DTS does ALS account for? Just looking at this. Yeah, roughly 16%, right? And similarly, DERS accounts for what percent of variance in DTS independently? What bivariate association? 0.5 squared is 0.25, right? So about 25% of the variance, yeah. And those give us kind of nice measurable aspects of effect that we can understand. Of course, this R-squared, why is this R-squared higher than 0.16 that we just had? What's going on there? I talked about this, right? What's the difference here? Say that again? It's not quite redundancy. This is the difference between correlation and regression, right? This represents a regression coefficient. And the regression coefficient, what is our denominator? It's only variance in y, right? And for correlation coefficient, what is our denominator? Total variance, yep, x and y variance, right? Okay, so you wind up seeing an R-squared here that is slightly higher than what we see up there. Let's scroll down, and here's our regression model, right? In step one, we have a beta of minus 0.521, minus 0.521. If we come back up here, right? Same as our correlation coefficient. And this is really interesting though, right? Our beta coefficient for alls. So notice this minus 0.521, that is a bivariate association, right? It should match our correlation. It reduces a little bit when we put alls into the model, but alls does not predict our dependent variable at all, right? Here's our p-value, 0.784, but we know that they're strongly correlated. Where's our correlation table? Right here. 0.392 is a strong, significant correlation. What is going on here? So this isn't quite suppression, right? What is it? What did I say differentiates suppression from redundancy? Yes, suppression is generally when the sign winds up being flipped, right? Redundancy is when x1 and x2 are just redundant. They're so much the same thing. And in fact, here we have a correlation between x1 and x2 of 0.74, right? Which means that they're sharing like over 50% of the variance together. Like they're just basically the same variable. And so alls here winds up being redundant. If we do this, if we go analyze, regress, linear, and we remove alls here, remove ders here, and we just put alls in, what are we going to find? Before we do this, what are we going to find with alls? We're going to take yes. Statistically significant, and what will the sign be? It'll be negative, right? And let's add ders in step 2. Let's keep all of our model fit statistics checked, and let's run this and let's see what happens. Okay, so alls 0.392, and if we come down here into our first regression model, we should see the beta weight 0.392, right? And this is a beta weight, like I said, in single variate regression or bivariate regression, the beta weight and the correlation are going to be exactly the same. However, when we add ders in, it drops way, way down, right? So if we look at our zero-order correlations, these are our correlations that we would see in our basic correlation table. What is going on here with part and partial? What does this value right here tell us? So the part and partial are telling us that the relationship between alls and our outcome variable is completely gone, whether we're including the portion of variance that's also accounted for by x2, by DTS, or if we're including the entire variance of y, right? But basically, any relationship between alls and DTS is gone once we partial out the variance in either DTS and the outcome variable, or in DTS only, or total, I'm sorry. Does that make sense? And so one way that we can find this is an interesting point, because in a moment we're going to talk about mediation, and you see roughly the same thing in mediation. So how can you differentiate whether or not your model is mediation or whether or not your model is redundancy? Yeah.
If the correlation is not that strong, then it means it's with a
Certainly. So the higher the correlation between x1 and x2, the greater the likelihood that you're talking about some sort of redundancy, right? It's also possible, though, that the only way you can differentiate the two is from theory. This becomes a problem with causality, right, and trying to make a causal argument, because you can say that the reason that these two, that x1 and y are related, is because of x2. That's a mediation analysis. Alternatively, if all of your data is collected at the same time, it could just be that x1 and x2 are redundant with each other, right? They're the same thing, and x1 is not causing x2, which is in turn causing y. And so a lot of that winds up having to be a theoretical argument. Okay, let's try something else now. Instead of redundancy, let's go back and let's go analyze regression, linear. Let's remove DERs. Let's remove alls. And let's go aim. And then in the next step, let's go alls. I think this is what I wanted to look at. Hold on a second here. Okay.
Can I ask a quick question?
Shoot.
Like a clarifying thing. What is the difference between putting it in block 2 as opposed to putting more than one in block 1?
Yeah, that's a great question. So there's no difference. The real difference, if you put everything in block 1 and just hit go, you're going to get the same thing that you get in whatever you put in the last block, right? And so right now we're using block 1 and block 2, but you can use block up to 100, right? Or maybe more. I don't know how high it goes. But what it does do is it allows you to see what is the effect of adding one more variable, right? In a few weeks, we're going to talk about something called stepwise hierarchical regression. And there's a couple of ways to do that. One is to just iteratively add variables yourself through blocks. Another way is to do what's called an enter procedure and a drop procedure, in which the software will iteratively do that, enter and drop, enter and drop, enter and drop, to empirically find the best possible predictive model. There's problems with that I want to wait until we get to that class. But essentially, there's no real difference. It's just allowing me to kind of highlight things as we're walking through. When I write a regression paper, though, I will tell you, I'll say in step 1, we regressed y onto demographic variables to control for age and gender and blah, blah, blah. In step 2, we entered the predictor variables of this, 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 and this. And we saw a change in f of this and a change in r squared of this, right? Indicating that this model fits superior or explains significantly more variance than demographics alone. In step 3, we might add interactions between the variables before, right? Or we might add some other variable of real interest. So sometimes what you're doing is just saying, like, we're going to control for this, now we're going to control for this, now we're going to enter the thing that we're really interested in. It allows you to do those types of things and make decisions about whether or not, when you do those, if your explanatory variables or predictor variable has a measurable effect above and beyond what's already explained by other things, right? So, yeah. All right, so let's enter those, and we have our part partial and such, and click OK. All right, the correlation with distress tolerance here is minus 0.026, and it is not statistically significant, right? 0.247. The correlation with this is affect intensity with affect lability is 0.4. That's a decent correlation, you know, accounting for 16% of the variance in each other. It's not a ridiculous amount. of variance, and it's unlikely that this at 0.4 is going to be a redundancy. So let's scroll down. They are related though, right? There is our model R squared. We have 0.026, adjusted R squared. That looks like a negative value. I wouldn't use a negative R squared because technically that doesn't exist, right? This happens every once in a while when they do a mathematical adjustment for variance. But true variance will never be negative, with one exception. Anybody know the exception? What that is called when you wind up with a negative variance? It can happen. It happens usually in things like factor analysis or something, and it happens because of things like suppression and multicollinearity. But anybody know? It's because variance is not a linear construct, right? So unfortunately, you can wind up with negative variance when you have a lot of multicollinearity, a lot of overlap. Anybody know what that's called? It's called a Haywood case, and that would be an ARM 3 thing anyway, not an ARM 2 thing, but just for your information. All right, so let's scroll down to our regression model now. Let's start here. We have minus 0.026. That should match our bivariate correlation, minus 0.026. It does. Perfect. And it is not statistically significant, right? 0.494. So affect intensity does not predict how well you tolerate distress. That's interesting, right? And then if we look at our next model, something happens. We added affect lability into this, and what happened with affect intensity? It became significant, and it did something else. It reversed signs, right? And when something reverses signs and all of a sudden either has a meaningful effect or no meaningful effect, we call this suppression. This is suppression. What's going on with suppression? Who remembers what I had said? So suppression is when the amount of variance that's left in Y, right, gets reduced so much because of your other predictor variable that you find some sort of counterintuitive or sometimes sometimes intuitive association between x2 and y that normally isn't there, that you don't find in a bivariate analysis. And it's because that the denominator in your variance equation gets reduced so much, right? So, yeah. All right, last thing that we're gonna look at with this data, and then we will flip to a different data set is, go ahead, do you have a question?
Yeah, I just had a question about the part and partial.
Yeah.
Is that related to the partial and semi-partial?
Yeah, it's so,
How do we make sense of that?
part is what I call semi-partial. Partial and partial are the same. And then your book calls them partial and semi-partial. And in SPSS, they call semi-partial part. Yeah. Okay, let's do one last thing. We've talked about redundancy and we've talked about suppression. But let's do something here that I think is interesting. Regression. So go regression, linear. And let's remove our predictors. Let's remove all of that stuff. And let's go audit tote. Or I mean yak tote. That's alcohol problems. PBS. This is behaviors that you can use to engage in to reduce problems. and alcohol consumption. And we hit OK. When we look at our correlation coefficients here to start with, we can see that PBS is correlated with yak, and drinks is positively correlated with yak. So the more PBS you use, the fewer problems. The more alcohol you use, the more problems. And PBS is actually correlated with alcohol use at almost the exact same level as it is with alcohol problems, right? If we scroll down, in a bivariate analysis, we would expect the beta for PBS predicting alcohol problems to be what? Negative and statistically significant, right? And here it is negative, and it is statistically significant, and of course it matches the correlation. Now, if we add drinks to this, it's no longer statistically significant. Our p-value is now 0.053. Drinks is a very strong predictor of alcohol problems. We could call this what? So it looks like, sort of looks like what when we first started? It sort of looks like redundancy, right? Like maybe these two things are just so strongly related that when you account for this other thing, when you account for drinks, PBS no longer predicts whether or not a person has problems or not. However, the correlation between PBS and drinks was what? Between PBS and drinks.
Minus 0.164.
Yeah, 1.6. That is not a big correlation, right? So I'll tell you what PBS are. They are behaviors like alternating between alcohol and water when you're out drinking, adding more ice to your drinks so that you drink less, setting a limit on the number of drinks that you're going to have. These are theoretically consistent things that should predict lower rates of alcohol use, right? And subsequently, these things should then lead to lower rates of alcohol problems. And so this is, yes, a mediation analysis. Well, where redundancy looks something like this, right? Mediation actually looks like this, where the relationship between this x1 and y is because of x2. And in some cases, this isn't even there. And I talked about that in the video, right? There are instances in which mediation does not even have to show a significant relationship between x1 and y in a bivariate sense, but we do see it in a multivariate sense. So yes, this is a mediation model. We are going to talk a little bit more about mediation coming up in a few weeks, but we're missing one piece here, and that is we can look at this in a simple correlation and say that alcohol is associated with or PBS is associated with alcohol, right? But we're missing the basic regression model. Who did the reading, just out of curiosity, for today? Who read that article, the Barron and Kenny article that I posted? So in that Barron and Kenny article, they lay out these steps. And the first step is what we did here. You look at the relationship between PBS and problems, or ultimate outcome, right? What's the second step? Anybody remember?
Put together.
Not quite. The second step is to look at the relationship between, between alcohol use and problems. The third step is actually to look at the relationship between PBS and alcohol use to make sure that we have a path there, though that, I mean, yeah, the first step isn't actually necessary in order to claim mediation. But and then the last step is you put both of those predictors in the model, and you have two different types of mediation. You have full mediation, which is what we see here, when the relationship between PBS and alcohol problems disappears. It's no longer significant. It is fully mediated by alcohol use. And we also have something called partial mediation. And what would partial mediation be? Anybody want to take a stab?
When there's still a direct effect, but it just
Say that again?
it reduces the direct effect, but it's still
Yes, the direct effect is diminished, but still statistically significant. And so in this case, a partially mediated effect would mean that that p-value was 0.043 instead of 0.053. Just out of curiosity, what's the difference between 0.05 and 0.06?
Type 1, the probability to reject the null hypothesis based upon the type 1 error. We assume that should be the maximum by which we get to the
Yeah, and in the end, right, what we're saying with all of this data is that we've drawn a sample from a larger population, right? And alpha of 0.05, if we're trying to reject the null hypothesis, what we're really saying is that it is a 5% probability that we drew this sample from the tail of a distribution, right? From one tail or another. That means there's a 95% probability that there is some sort of an effect, right? But there's a 5% chance that we just drew a sample that gave us this result, right? That's really what your 0.05 is saying. So if it was 0.06, then you're saying what? There's a 6% chance, right? And we, not to be a complete, no, it was, we were doing this just to be smartasses. I'm going to read you, I'll read you something that we just had published in a paper. So we had done this analysis, and we found a significant interaction, and the p-value for that significant interaction was 0.034, right? And that was in like a baseline model. If we controlled for age and for gender, they had no effects in the model, but our p-value for our interaction became 0.053. And so, oh, I'm sorry, it was 0.056. We had put a note in there for this. It says the variables age and gender were initially included in the primary analysis. Neither age, p equals 0.552, nor gender, p equals 0.087, predicted alcohol use consequences. However, when the variables were included, the interaction between narcissism and PBS no longer reached traditional levels of statistical significance, p equals 0.056 versus p equals 0.037 when excluded. Consistent with Rosnow and Rosenthal's 1989 assessment, we want to underscore that surely God loves the 0.06 nearly as much as the 0.05. And I can't believe they published that. But anyway. Yes, this is an example of a mediation model. And in a few weeks, we are going to talk way more about mediation than you guys are ever going to want to hear about. But just as an FYI, when it comes to writing most papers, understanding partial correlations is less important for the paper. It's more important for understanding whether or not you have suppression, whether or not you have redundancy, or whether or not you can make a claim about mediation. But almost never do you see anyone talk about part and partial correlations. It winds up becoming an important piece of your regression diagnostics when you're doing your analysis to try and understand the relationships between these variables. Next class, we're going to talk about visualization of data. So Kelly, you should enjoy that, right? and I think the statistical equivalence of well, have you tried turning it off and turning it back on again? Is, well, have you tried looking at your data, right? And so this winds up being an important piece of it next time, and we will talk about looking at these part and partial correlations and what things should look like when you do that. But for right now, just understand what they are is partialing out various aspects of variance in all of your independent variables as well as your dependent variable, whereas beta coefficients are simply concerned with the dependent variable, right? All right, let's take one. Actually, you know what? Let's not. Let's push through here, and then we will wrap up a little bit early today. Sound good? All right. The last thing that I want to talk about is multicollinearity. So let's grab the last data set. And it should be called something. I think it's called class data 2 or something like that, right? Oh, I'm opening it in the wrong thing. No. There we go. Week 3, class 2, open. So in this data set, did I rename your guys's to look like this? Do they say BAC, social, tension reduction, liquid courage, sexuality? Okay, what these are measures of blood alcohol concentration over here. And then alcohol expectancies. These are things that you think will happen to you when you drink. And this is Mark's area, actually. And what we do know is that these things tend to predict how much a person drinks, and how intoxicated a person gets when they do drink. And in Mark's, in Mike Dunn's lab, where Mark works, they have this intervention to try and change your alcohol expectancies. And it's fantastic. There's this great video of this kind of pioneer in alcohol work who Mike worked with as an undergrad, where people come into a bar lab. And I know this is a complete aside, and just bear with, I do this. Like, Torre's sitting here thinking, like, I've seen this before. I know where we're going. So they come into a lab that's set up like a bar, and you have about 15 people, and they all get screwdrivers, right? Which is orange juice with vodka. But they don't all get screwdrivers. They all think they're getting screwdrivers. Some of them are just getting screwed because they put orange juice, and then they just put like a little thimble of vodka on top or around the rim. And so it smells like alcohol, and at least on first taste, it tastes a little bit like alcohol. And they all start drinking, and they all think that they're getting drunk. And before they do this, they rate what they think is how they think they're going to feel when they start drinking, right? And then later they rate how they actually feel now that they're drinking. And amazingly, those two things match up pretty well. And then the investigator says, okay, surprise, you and you had alcohol, you all did not, right? And it changes your expectations of what happens when you drink, like doing this small piece. And so we're not looking at that data. All we're doing is looking at like the expectancies and BAC. But it's cool stuff, and that's just an aside. But all of these things should actually predict BAC. So let's go like this. Let's go analyze. And correlate. Let's just do bivariate correlations. Oh, you can do partial here. I was telling you guys about this, right? You can do partial, but you can't get part. So if you look at partial correlations here, you can look at the relationship between BAC and social, controlling for any of these other things. Why can't you get part? Yes, because part is assuming something very specific about the dependent variable, right? It's assuming that you are retaining 100% of that variance in the dependent variable, and partial is removing all overlapping variance. So, all right, don't do that though. Let's go analyze, correlate, bivariate, and let's just throw them all over. So you can do that by holding down, I think it's Control if you're a Mac. I'm the only Mac person in here right now, so doesn't matter. And hit go. And this correlation table looks a little bit different than the correlation table that you get with regression. When you do a regression analysis, they break up your correlation coefficients, your R's, into the first block of the table, and they break up your p-values into the second block of the table. But if you just do a correlation analysis or correlation table, then it puts them all together. Anyway, if we scroll down through BAC, we see, come on, get out of there. We see that social is positively associated with BAC. Tension reduction actually is not. Liquid courage is strongly positively associated. Sexuality is positively associated. And tension reduction is sort of associated, just not very strongly. Then if you look at the correlation amongst all of the expectancies, they're very high, right? They range from 0.4 to 0.72. So we're going to expect something here. And what are we going to expect to happen? At least some redundancy, right? Let's.
The cutoff when looking at these correlations for redundancy, so we're around 0.4.
There is no set cutoff, right? This is one of those things where you have to kind of use your best judgment on that. 0.4, correlations of 0.4 actually aren't the worst. Really, you wind up having to dig into the regression diagnostics and say like, okay, so if this is in the model and this isn't, then these things are correlated just fine, or this predicts this thing just fine. However, when I add all of this into the model, then it no longer predicts, and that's how you start trying to understand whether it's redundancy or mediation, right? In this case, these things are all assessed at the same time, and they're all assessed in roughly the same way. This is not going to be mediation. This is going to be a type of redundancy, and it's a redundancy due to multicollinearity. So let's go analyze regression. Linear, and let's predict blood alcohol content. Oh, you know what? Let's do one at a time. Let's do social first. Actually, let's not do social first. Let's do tension reduction first. And then let's add, in the next block, let's add social. And in the next block, let's add sexuality. And then in the last block, let's add liquid courage. What's liquid courage? Not a drinker, huh? No, I'm just kidding. I think this, yeah, it's when you start drinking and you feel like you can take on the world or the biggest guy in the bar, right?
The confidence you get.
Yeah, it is. It's the confidence that you get from drinking. Yep. Yeah. And so one of the expectancies that people have is that if they start drinking, they'll be more confident, right? They'll, yeah. It's really interesting, isn't it? Because if you ask people, like, if you think about of these different things, being more social, removing tension, increasing courage, or making you more sexual. Which of those do you think would be the strongest predictor of how much you drink? Okay, who says social? Okay, so we have a few people that say social. Who says tension reduction? Same roughly as social. Who says liquid courage? Okay, and who says sexuality? Everybody's like, don't make eye contact.
What is the sample?
This is that's a great question, right? If these are all people with raging alcoholism, then it's different, right? If these are all college students, this is a college student sample. Although they are, I think this was just I think freshmen actually. Anyway, amongst freshmen, what would you say would be the most important thing here? That's interesting. I would not say social. I would, yeah, young 18-year-olds, right? Yeah.
I feel like at 18 you don't need
But yeah.
If you're a guy, yeah, you don't, because you're not.
Okay. If you have an alcohol use disorder, though, if you have alcoholism, definitely tension reduction is very important. So, all right, let's hit go and let's have a look at this. So there are our correlations, right? And here's the correlation table that should look exactly like what we had before, and then the p-values for those correlations down here. And recall that this correlation, tension reduction, was not statistically significant in this group. All right, let's move past that for right now. And let's come straight down to our regression table. So we see in step 1, we added tension reduction. I added tension reduction on purpose because I knew that it was not a significant predictor of BAC. And we see that that's the case here, right? Not a significant predictor. And our beta coefficient is 0.14. In the next step, we added social. Social, not a significant predictor. That's interesting. Also, this is very non-significant. It goes from a correlation of 0.14 to 0.02, right? Next step, the sign of tension reduction flips. What do we call this? That is suppression. None of our p-values are statistically significant. And finally, we add in liquid courage. Oh, surely. But notice, in this model, none of these things are statistically significant. Now, the problem is we know from our correlation table that some of these things are like strongly correlated with BAC. Like, look at this, 0.34, that's a strong positive correlation. Yet, when we account for all of these other things, it doesn't predict anything. So what do we say in an instance like this? Do we just throw our hands up and say, actually, I guess expectancies don't predict alcohol use? There's a problem inherent in this, right? What's the problem? It's that all expectancies predict alcohol use, and they predict them in roughly the same way. And so if you put them all in the model together, then all that overlapping variance removes any predictive value of expectancies. There's a few different things that you can do in this instance. What's the first thing that you could do? Anybody want to take a guess? What would you think is the first thing that you could do? That's the second thing. The first thing, the simplest thing, and the not recommended thing would be to do what?
Separately.
Run them all separately, right? Yeah, you could do that. There's a problem with that, and what is the problem with that? Yep, you inflate your type 1 error, right? Absolutely. You could do a correction for that. There are a couple of different types of corrections that you could do. What's the second thing that you can do? We could call this actually we could call that first one 1A and 1B because I hate both of these things. You could do the separate analyses for each one. You could also just pick the strongest one and say these things are all highly correlated and thus this seems to be the most important one. There's a problem with that as well. Rita, want to take a guess? What is the problem with picking the strongest correlated one here? The problem with that is that these correlations are based on a sample. And this might be the strongest correlation just in this sample. And you might collect another sample, maybe a sample of alcohol use disorder people, maybe another sample of students, and you find out that social is the strongest predictor, right? And if you're doing that, you're losing something important. And what is that important thing that you're losing? You're losing precision of your prediction, right? You're basing your prediction off of a randomly generated highest variable, which may or may not be the highest variable. You don't know. The third thing that you can do was what, Sarah?
Combine.
Combine them. How do we combine them? What?
Variable.
Okay, so yeah, if you're going to go there, we'll go there. You can combine them making a latent variable, right? Absolutely, you can do that. What's another way that you can combine them? Yeah, you can take the average of them, right? You can just make a mean. So let's do that real quick. Let's see what happens.
Can I ask a really quick question?
Yes.
You disclosed it. You have asterisks that show you if it's significant or not. How
Sure.
do you get those? What did you do that shows up? Because it doesn't show up on.
I did absolutely nothing. I just did it. Who does not have asterisks? I have no idea. I don't know why that happened or doesn't happen. Okay, let's do this. Let's go transform, compute, and let's. Did everybody see what I did there? Are we all tracking? Let's make our target variable called expect, and expect should equal. You can scroll down here for your groups, but I think you can just type mean here. Is that right? Can you type mean or do you have to type average? Let's try this. I think that this works. Nope. Oh, incorrect variable name. Either the name is more than or it is.
Comma is required, like comma between the variables.
Oh, is that the deal? Oh yeah, that looks like they put them all together. So I need to put a comma in here.
You have send with encourage?
What?
Like,
Oh.
Yeah.
Oh, hopefully that fixes it. Is it working for other people? Is that why you know that mine's just, I'm just a soup sandwich? Who knows what a soup sandwich is? Yeah. It's a mess. All right. So now we've created a mean, and we can go analyze, regression, linear, and we can remove all of this junk, right? And we can add this in. That's all we have to do. We hit go, and as you might expect, we see that expectancies are strongly predictive of BAC. Our p-value is 0.003. And of course, our zero-order partial and everything is going to be exactly the same because basically in a model like this, it is a bivariate association, right?
So would this be the recommended approach?
So let's talk about this for a second because I think this is an important piece. Who has seen these diagrams that say like, if your data is this, you should do this, and if it's this, you should do this, and if it's this and this, then you should do this? Who's seen those before? Right? Like these flow charts that tell you like, oh, if you have this and this, you should do an ANOVA. And if you have this and this, then you should do a multiple regression. And you guys have seen these before, right? Like, I'm here to tell you that almost all of these statistics that we're going to learn have the same underlying mathematical formulas. And so if it says you should do an ANOVA, you can do that in regression. And if it says you should do a logistic regression, you can do it in a multinomial analysis, right? So what was the question? What got me started on this? The take-home message here is that there is no one analysis or no one model that can't be replicated in some way by some other model within the kind of general linear model framework, okay? And so I don't want you to get too hung up on like, oh, should I be doing a regression here, or should I be doing an ANOVA, or should I be doing this, or should I be doing that? Because we can get to the same spot, right? And in fact, what do I have for data here right now? Shoot, I don't have anything. Okay, let's do this. Well, we'll do this next time. I do want to show you guys, and I'll show you this next time. But if you have like a dichotomous variable, gender, which is in our other data set, if you do a correlation and a regression model with gender predicting something and a t-test between, like, we had affect lability, right? If you look at the correlation between gender and affect lability, and then you run a regression with gender predicting affect lability, and then you do a t-test on affect lability by gender, what you're going to find is that the p-value for your correlation is the exact same p-value that you get in your regression analysis and in your t-test. If you do the t-test in the ANOVA, or a t-test in an ANOVA, you will find that, and a regression, you will find that the t in your t-test and the t in your regression analysis are exactly the same, as is your p-value. And then if you look at an ANOVA, you will find that your t matches your f, assuming that you square t, right? Because f is t squared. So if you run a t-test, you can square that t, and you will get the same value that you'll get for f in your ANOVA. All of those models, correlation, regression, ANOVA, and t-test, they're all the same thing, right? They all have the same underlying math. So anyway, this also means that, and I will post this for you guys, this also means that we have these measures of effect size that people associate with an ANOVA. What's the measure of effect size that we typically associate with ANOVA? Eta squared or partial eta squared. The effect size that we associate with regression is r squared, right? With a correlation, the effect size is the correlation, it's r, right? And with a t-test, the effect size is what? What do we usually associate with a t-test? It's called a Cohen's d, right? All of those effect sizes are interchangeable, and I'll give you guys an effect size calculator where you can plug in Cohen's d, and it will tell you what eta squared is and r squared and all of these other things, right? Like it's very easy to move back and forth between those, which means that you can, in a paper, if you have an r squared and a reviewer wants to know, well, what's the Cohen's d for that, you can do it. You can give them a Cohen's d, right? But yeah. All right. The final way, just FYI, which Manny already said, is to form a latent variable. You guys know what a latent variable is, right? So when we're drawing these things out, we have x1 and we have, x2 and we have y. And when you draw them out like this, you draw them in squares, and these squares are called observed variables, right? They're measured. We have a true value for them. But in psychology, and perhaps in areas that are not, we have this underlying idea that we're trying to measure something that you can't really measure with an observed variable. For example, I look at impulsivity a lot, right? And so I'm trying to understand what a person's level of impulsivity is, and I understand that I can give them some measures of impulsivity, right? x1, x2, x3, and those measures are actually driven by some sort of construct that I can't really measure that underlies all of that. And that's impulsivity. And impulsivity is a combination of all of these things plus something else, right? Anybody know what the other thing is? Anyone guess? Plus error, right? Yeah, plus error. Because we can't measure anything perfectly. Now this becomes a problem in regression because one of our assumptions with regression is what? It is that these things actually don't have error, that they're measured perfectly, right? And so frustratingly, that means that the only real error in regression is residual. right? This winds up being something that we have to think about when we start doing our analyses and start talking about the results of our analyses, is the extent to which our measures are really tapping into the construct that we say that they are. And this is called what? Yeah, it's validity and reliability, right? So yeah, that should have been something that you guys covered in ARM 1, right? And this is why in every methods paper, in every research paper, you have a methods section where you address validity and reliability issues for the measures that you have, right? So the nice thing about latent variables is you assume that it's not measured perfectly, and then you can use this to predict whatever you're trying to predict. All right, guys, that is all I've got for today. I will get your homework up shortly. Other than that, oh, do you guys want to go through homework quick? Do you just want to talk about it while we're here? Sure? All right, let's do that. I'm going to turn the video off. I don't think we need it to talk about homework.